Okay, so our next speaker is Julian Barrier. He is from the Institute of Photonic Sciences, and his presentation is entitled Robust 1D Proximity Superconductivity Along Graphene Domain Walls in Quantizing Fields.
Thank you for the introduction. Actually, the work was done when I was working in Manchester, UK. So before I run out of time, let me thank the people who've been contributing to this work. Here, Najin led the fabrication of devices, and Andre sponsored the project. Let me start by introducing Andreev bound states in a magnetic field. So if you take an SNS junction with graphene, for example, in order to induce a flow of Cooper pairs between two superconducting electrodes, you will create Andreev bound states of electrons and holes trajectories. So experimentally, you can see a zero voltage state, or in DVDI, which is our measurement of choice, a zero resistance state and a critical current, at the critical current peak in the resistance. Now you start applying a magnetic field, and your electron and hole states start to bend. It's not a problem as long as the distance at which they merge at the superconducting to normal interface is smaller than the superconducting current's length. Experimentally, what you see is that the critical current is modulated by the junction area through this sort of Fraunhofer pattern. Now you increase even more the magnetic field, and your electron will bounce off the superconductor, create a hole, but this will never merge into a closed trajectory. And in traditional 2DEGs, the critical current was generally destroyed at that field. In graphene, however, which has a relatively high mobility, you can have closed trajectories that happen thanks to scattering along device edges, and which result into these mesoscopic fluctuations of the critical current at that sort of field. Now you increase even more the magnetic field, and electron and hole trajectories propagate along edges of the device. And they happen to be at very large distances if your device is very large, which, if you want a high magnetic field superconductor, it has a short current length, and this won't be enough to couple edge states, and all the supercurrent will be destroyed. However, this presents interest, as theoreticians have predicted, that this could host Majoranas or non-abelian hanyons or whatever you fancy in this regime. So there was a lot of research in this field, and particularly in the group of Gleb Finkelstein at Duke University, who have observed in the quantum Hall regime, so here you see a clear quantization of the conductance at high bias, that they could have, in graphene devices, superconducting pockets that emerge there. The original idea of this experiment was that electron and hole pairs on opposite device edges would be coupled via Carroll-Andreev edge state, which is a hybrid of electron and hole propagating in the superconducting sheath. Now they pushed the experiment a bit further, and they actually realized that was not the case. In fact, electron and hole trajectories would form on both edges because of defects along the edges. But having learned from all of this, the group of Benjamin Sassepé in Grenoble made very recently devices that were very narrow with graphene flakes that were not etched, so purely for exfoliation, which preserved the very high quality of the edge states. And they managed in these narrow devices to couple edge states through chiral states here. And they realize critical currents of a bit less than a nanoamp at magnetic fields of 6, 7, 8 Tesla, which is a really impressive experiment. However, there were prediction and theoretical work that said that how good this was, this would not allow topological superconductivity. So we need to think about something else. Our idea that we could try to couple two edge states, not on far edges, but in the center of the device. So we created a very narrow slit in the device center of about 10 nanometers, which is the comparable to the current length of niobium titanium that we use. We made Josephson junctions, we measured the critical current at high magnetic fields, and we observed nothing. There was no critical current in the quantum Hall regime here above 2 Tesla. We tried the same thing with wrinkle and the graphene devices that's shown on the bottom, and same thing, we observed nothing. So we had another idea, which was to use domain walls in graphene. So if you put two layers of graphene on top of one another, they will arrange into a large network of AB and BA domains. And at the center, you'll create a domain wall. Our idea was that you could have a quantum Hall effect on one side, quantum Hall effect on the other side, and the two edge states coupled in the middle on each side of the domain wall. So we use niobium titanium because it has high critical field, and we apply a perpendicular magnetic field to induce cyclotron motion. Let me start here by just showing normal state transport. We measured Landau file diagrams at high magnetic field at temperatures above the critical temperature of the electrodes, and we saw the degeneracy expected for bilayer graphene. But the resistance, and particularly the conductance here, was different from what we expected. It was sometimes twice, 3 times, 4 times higher than what we expected. Here I show the 2-probe resistance of a device with no domain wall in graphene at high magnetic field. And what we saw is that there's a gap that's opening in these devices with a resistance that varies with time, with the temperature. If we add one domain wall in the middle of this junction, we observe that there's no gap here, and the resistance is much lower. Now we focus what happens for one domain. We focus what happens at the 0th Landau level, so at density here, 0 density. And what we observe is this activated behavior for 0 domain wall, but for one domain wall, the conductance saturates at about 40 square over 8, which suggests there are 4 electronic modes in this device. And if we add more domain walls, then what we observe is the conductance saturates again at multiples of 4 square over h. Now we look at in the quantum Hall regime at we look at the Josephson coupling at low temperature. We have clear resistance. We have Fraunhofer patterns that show that the supercurrent propagating indiscriminately everywhere, whether there's no domain wall or domain wall. But in the quantum Hall regime, this becomes interesting. We have this sort of pattern where here the most important thing is that the critical current remains constant over a very large range of magnetic fields, as if it was stabilized by the field. This is a 0 resistance everywhere. And below that, we sort of have very strong beating pattern, very strong interferences here, which probably show interferences between domain walls and the edge of the device. And importantly, there's no beating, which suggests very narrow channels created here. Comparison with 0 domain wall, there was no supercurrent above 2 Tesla. Now we created junctions with 0 domain wall show at 3 Tesla over a few hundred Gauss. What happens, there's no critical current in these control devices. We add 1 domain wall, we have this constant critical current. And now we had 2 domain walls separated by this distance small w here. And what we see is this squid-like pattern with very clear interferences. 2 things. The first is the critical current that we observe. The amplitude of these oscillations is twice the critical current for 1 domain wall. And then there's a correlation. If we add more domain walls, we have this linear dependence of the critical current with the number of domain walls. The beating pattern can be related to the size of the device. It corresponds exactly to what we have for the separation of 2 domain walls. And we have this almost perfect squid-like pattern with no critical current in the middle, which suggests that 2 domain walls carry the exact same amount of a supercurrent. Now I'm going to skip a bit these Fraunhofer oscillations because I'm running out of time. Our theoretical collaborators have shown that the electronic states within these states corresponded indeed to hybridization of Landau levels with electronic states within the domain wall, and that they are separated by distances less than a nanometer. And as a conclusion, I hope I convinced you that we created a sort of novel system, novel 1D system to study superconductivity. It could be a platform for current standard through the study of quantum phase slip. One can also imagine having topological quasiparticles by studying the fractional quantum Hall effect in this system, or even use it in the normal state without superconductivity to study Luttinger liquids, for example. Now, thank you very much for your attention, and I'll be happy to take questions.
Oh yeah, there's a question right there.
Hey, thanks for the nice talk. In the diagram where you showed the squid-like behavior of the critical current, do you know what the flux periodicity is? So that's the flux density, but do you know what the flux is? Is it h over 2e, h over e?
Oh, so here there's nothing topological in this system right now. We have ideas to make it topological, but the main drawback from this study is that we have non-chiral states. Because they're due to this hybridization of Landau levels, they're due to this hybridization between Landau levels with the electronic states within the domain wall. We have a combination of chiral and non-chiral states. We're working on trying to make them purely chiral there. So there's no periodicity, no fancy periodicity here with the flux yet.
Yeah, thank you for the talk. I had a question. So why do you think you see this effect with the different stacking the bilayer regime and not when you were making a crack in your single layer? Do you think it's due to the bend structure change for the bilayers, or the bigger distance, or the disorder?
So the distance, we actually try to have a distance comparable to this. Okay. I think it's the fact that the edge states couple very weakly to the superconductor, and what we have is, as soon as we're able to create this hybridization of edge states with other electronic states, then it becomes much more transparent to the superconductivity.
Okay, so it's the gap is not basically enabling coupling sufficiently.
Probably.
Okay, thank you.
Thank you.
Okay. Okay, so we're out of time. Let's thank our speaker one more time.